Both of us?
Can you hear me?
One?
Hello.
Okay, great. So the next talk is about Code-Specify-Test-Debug-Prove presented by Zain, Aamer, and Hiroyuki Katsura.
Thank you. Yeah, I'm Zain. This is Hiro. We'll be talking about Code-Specify-Test-Debug-Prove. And so our motivation is that we want greater assurances about system software written in C. System software because it's heavily relied upon. C because you get limited guarantees. And so how might we do that? One approach is to use formal verification, where the user writes rich functional specifications. These are in the form of precondition, postcondition pairs. And the properties we care about are memory safety and functional correctness. And so one issue that's historically been the case is that this is typically all or nothing. So there's a large period of time where the user is iterating on the specifications where they don't get much assurance. And then once the proofs start to go through, they start getting that increased assurance. Another issue is that this is an inefficient feedback loop. And so the user writes the specification, they run the verifier. If there's a failure, they then debug that proof failure. But the simple question, are my specifications correct, is like hard to answer because failures may be due to missing annotations, not just an incorrect specification, and so such as loop invariants. And so we propose an incremental workflow, which is going to build upon the standard code test debug cycle. We're going to focus on specification writing and testing, and this allows us to combine testing and proof in a single framework. And so this is the titular Code-Specify-Test-Debug-Prove. And so focusing specifically on the specify-test-debug portion, the user will write specifications, but rather than running the verifier, they will run testing. They will look at the testing failure and then see if there's a bug, refine their specifications. And so considering the question that we had looked at previously, are my specifications correct? In this case, you get incremental assurance as more tests pass and classical measures like coverage increase. And then if there is a failure, then that failure will in fact be due to a discrepancy between the specification and implementation. So the full workflow looks like this, where the user is going to write a specification, they're going to perform testing, they're going to iterate on the test failures. Once all the tests pass, they will then move on to proof, and they will then debug that failure and then potentially get a complete proof. And so our graph becomes a lot more gradual, where we start off with unit and system testing, where we're going to instrument existing tests to check the specifications at runtime. We're going to apply random testing. We're going to take the precondition, generate random inputs based off of it to exercise that instrumentation. And then we'll get the full proof at the very end for the maximal assurance. And so one option for choosing a toolchain would be Frama-C. It does support runtime checking of specifications. However, it uses first-order logic, and we want to capture quite complex memory ownership patterns. And so we will look at the CN toolchain, which uses a restricted fragment of separation logic. This allows us to reason about these ownership patterns. And this fragment's already been shown to be good for runtime checking of specifications, random input generation, and formal verification, which were the 3 points on our graph. And so we had to do a bunch of technical contributions to get this working. And so one of those is various improvements to the instrumentation. This include adding support for a bunch of CN and C features, as well as improving performance, both in terms of memory usage and speed. It also involved the implementation of a new random testing tool, which uses an SMT solver, so it can handle quite complex point arithmetic constraints. We also added support for ghost arguments, improved the verification speed, and we also did do a lot of engineering to make sure that this instrumentation worked in a bare metal environment. And so why a bare metal environment? Well, we had a case study, which is the PKVM HIP allocator. And so PKVM is a real-world hypervisor for Android developed by Google. It enforces memory isolation between the kernel and guest VMs, the main thing being that it handles sensitive data. It runs in a bare metal environment, so there's no C standard library, limited stack size. And so this really limits how it adds a lot of complexity to what the instrumentation has to be able to do in order to have like full system testing. And so we specifically looked at the HIP allocator, which is an allocator that supports malloc and free. And so how it manages memory is it uses a doubly linked list of these chunks. So here we see 3 chunks, has a header, some data, red used, and then green means that it's free. And so if the user asks for an allocation, potentially we assign that last chunk and return it back to the caller. And so we want to somehow track this ownership. And so we'll consider specifically an internal function, chunk install. And so it's going to take existing, which is going to be a pointer to an existing chunk that's free. It's going to take desired. This is a pointer inside of existing's buffer. And then it's going to split off a portion of that buffer to give us a new chunk at desired. And so a possible precondition, though perhaps this is too weak, wink, wink, is that we just want ownership that existing points to some chunk. We then, after running chunk install, have this new desired chunk. And so one thing that we want to say is that the chunk that existing points to, which is now different, C1, is disjoint from desired. And this, we get this via separating conjunction, so from our separation logic. And so now Hiro will walk through how we can iterate on this specification.
Hi, can you switch this? It's working? Okay, sure, I'm Hiro. And then now, like we've got initial specification for CN, like a chunk install. Then what we want to do here is to like sort of, I will show you how our workflow works for the actual chunk install example. Especially the key point here is that like a gradual assurance. So first we try to use specification as instrumentation and then try to test the implementation by using some unit test cases. Then if you want to get the higher assurance, then we try to apply random testing and then finally prove the correctness, this gradual assurance. So the first step is going to be to use the CN specification as runtime checking. This means that like our machinery automatically converts CN separation logic specification into C runtime checks and then attach these checks with the original program. Then we run the instrumented code with unit test cases. This allows you to track the ownership state and specification constraints at runtime. And especially for the previous initial specification for chunk install, if you run the implementation, then the implementation accesses the memory that the specification doesn't own. Then it will show some error like this. Especially, in this case, it's going to be an ownership error. And then the error message show you like what was wrong with the with the specification. Especially in this case, this address seems to be suspicious. Okay. Then the next step is going to be debugging the specification. Especially our transformation gives you some instrumentation in the C program. You can actually utilize the conventional debuggers such as GDB or LLDB to understand the situation and inspect the program. This is particularly useful because we can print the abstract ownership state in addition to some concrete pointer values or backtraces. Especially in this case, we can show some backtrace of a function, and then you can finally find out, okay, the next pointer of this function seems to be suspicious because this pointer is close to the pointer that you saw in the previous slide. And then probably after some debugging session, you will find out the root cause of the specification. Especially in this case, actually chunk install updates the back pointer of the next chunk. So in that sense, we have to precisely handle the behavior. Okay, it's working. Okay, sorry. It's in order to capture the behavior. I mean, you have to state the ownership of the next chunk in addition to the current chunk. So in that sense, in order to fix this situation, we have to add this ownership statement in the precondition. This is how spec test debug cycle works for chunk install, and then you can refine the specification further and further by applying this cycle. Furthermore, so far we have been using some unit test cases, but actually our specification instrumentation works in the hypervisor itself. This means that we can replace the heap allocator itself with the instrumented version of heap allocator and then run the PKVM itself. This is very useful because we can sort of test your specification and implementation in the actual environment, so you can see how the function is used or what kind of values are passed as arguments. And then especially this is difficult because PKVM is running in a very extreme environment. So you have to deal with some bare metal environment, so you cannot use some C standard libraries, like third-party libraries, or you cannot use some fancy printf functions or such kind of. Also, you have to deal with some very huge code because in the actual Linux build environment, if you apply preprocessed because of the macro expansion, your heap allocator is going to be like more than 130,000 lines of code or such kind of. And then our instrumentation machinery needs to deal with this code. And then the fact that our machinery is actually running inside in the hypervisor means that like, our machinery is practical enough to be used. Then, so far we have been using some concrete test cases and then we run the instrumentation code. But if you want to get the higher assurance, probably you might want to get more test coverage. And then for this case, you can utilize random testing. Because CN specification is a per function specification, sort of the high-level idea is that you can generate the test cases from the specifications and then test the situation by using the instrumented binary. And more precisely, we are on top of a separation logic. So from the separation logic specification, our machinery automatically generates the heap structures, and then we try to test the heap structure by using the instrumented code. For this case, we have a fixed specification for chunk install, right? And then from this specification, we can generate heap like this or like that. After you generate the heap structures, you can actually run the instrumented code, and then you will see, okay, this heap is fine, but this is not. And then after some debugging session, you will notice that, okay, desired pointer should be inside in the existing chunk. And then you will notice that, okay, you have to say in the precondition, desired pointer should be inside the existing chunk. Especially, we have implemented a new SMT-based testing generation program, and then this works very well with the edge cases related to some pointer arithmetics and complex constraints on pointers. Okay, after several iterations of these kind of spec test debug cycles, finally you will reach the saturation point where no testing machinery will complain about the implementation and your specification. And then now, at this point, we are ready to prove the correctness of the implementation. And the advantage of our framework is that we can use the same CN specification even for proof. This means that we don't have to switch to a new machinery, and then you can just use the same specification by adding some proof annotation and lemmas. Then finally you can prove the correctness of the implementation. So you can prove that the implementation actually satisfies the specification that you have developed by using testing machineries. Okay? Then maybe you can prove the correctness of chunk install now. This is how our workflow works for the chunk install example, but actually in this work we have applied this entire framework to the entire PKVM heap allocator. And in this campaign we have started with some sort of partial specifications for top-level functions, and then refined the specifications by using some testing machinery. And then testing machinery gave us some earlier feedbacks about the specification bugs, and then actually we could find 20 specification bugs during the campaign. Furthermore, we could find some 4 implementation bugs of the PKVM, and then all of which have been fixed by the Google developer already. And then in the end, we have verified the correctness of heap alloc and heap free retroactively, mostly without changing the C code. And this is what we have achieved by using the workflow. And then actually this can be achieved, and then in order to achieve this workflow, we have implemented a lot of things, and also we have developed some theoretical foundation for the workflow. But we don't have much time to talk about all the things, so if you are interested in this work, please read our paper. So let me conclude our talk. So we have proposed Code-Specify-Test-Debug-Prove cycle on top of CN separation logic. And this workflow itself is very practical in a sense that it works on real-world C code, and also the testing machinery actually runs in place in the hypervisor. And also we found that it was very useful in a sense that we could find many specification bugs without requiring us to actually try to prove something. Furthermore, everything is unified in the single CN specifications language, so we don't have to use a different machinery to prove something, and then we can seamlessly prove the things that we have developed by using testing machinery. Now everything is public online, like you can download the CN machinery from the repository, so if you're interested in, please download our machinery and use it. Thank you.
Any questions?
Hello. So I like to talk, and I'm curious. I don't know much about CN, but I assume that it's like specification, like it's like syntactically similar to C, right? Or yeah, could you tell me more about that?
It's closer to perhaps some like mix of Rust kind of. So like it has ADTs, for example, and so like for like a linked list, one would be like comparing the heap structure of a linked list, like traversing it, and then comparing it to an ADT list. And so then ideally your functional correctness is in terms of like a functional implementation.
So were the specs like handwritten or were they automated? So and were you testing these automated lifted specs?
So he wrote the specification. So the specifications are written by hand. And then the instrumentation, testing, and verification is all like running a command, and it happens automatically.
So could you be able to automate the specification making from the C code?
Well, so we've tried like quite a few experiments of like getting an LLM to do this, and it seems like it works surprisingly well, but
but that is not included in this
yeah,
talk.
that's not part of it.
Okay. Thank you.
Okay, then let's thank the speakers again.